Alright, today we're going to talk about Chapter 6, Part 3, Percentiles to Z-scores. So sometimes we start with the area or the percentage, and we need to find the corresponding Z-score or even the original data value. So I want to start right away with showing you an example and how to do this on the calculator. So let's say we want to find the Z-score that represents the lower 25% of our data. Just like we saw yesterday in part 2, we want to start with drawing a picture. So I'll have my normal model, my average at 0, standard deviation at 1, and I'm looking for the lower 25%. So I'm just kind of estimating in here, and I would always label that this right here should be 25%. In our calculator, what we're going to do is press second vars. And we went down to normal CDF yesterday. Today, since we're doing the opposite or the inverse, we're going to go down to number 3 where it says inverse norm. Now your calculator asks you for the area first. Although your calculator is very smart, it can only calculate areas going to the left. I'm looking for the 25th percentile to the left, so I can type in 0.25. My mean and standard deviation should again stay 0 and 1. I'm going to just jot this down here. So I have my inverse norm of 25%, 0, and 1, which my calculator tells me is a z-score of negative 0.67. Whenever we're working with z-scores, we always want to round to the nearest hundredth. So just a couple more examples here. What z-score cuts off the lowest 44% of the data? Again, we'll start with our picture. Mean of 0, standard deviation of 1. I'm looking for the lower 44%. So again, in my calculator, I'm going to type in inverse norm. The area this time is 0.44 with an average of 0 and standard deviation of 1. And we find this is a z-score of negative 0.15. Okay, now we're switching it up a little bit and looking for the highest 10% of our data. So I'll start with a picture. And I'm looking for just this little piece here of 10%. Now, when I go to use my inverse norm, we have to remember that my calculator can only calculate areas to the left. So left of the 10% would be 90%. So I need to type in 0.9 with the 0 and 1. And we get a z-score of 1.28. Okay, then the last one here is a little bit harder. It says one part of the SAT has a mean score of 500 with a standard deviation of 100. What SAT scores represent the middle 50% of the data? So I'll start with my picture again. I want this to be the normal curve, so I have a mean of 0 and 1, and I know that I'm looking for this middle 50%. Now your calculator is unable to calculate middle 50, so I'll have to figure out what's left over on this tail going to the left-hand side. Well, this whole thing has to add up to 100. 100 minus 50 gives me 50, and 50 divided by 2 leaves me 25% in each of these tails over here. So I'm going to start with finding this z-score over here on the left-hand side. To find that z-score, I would use my inverse norm of 0.25, 0, and 1. Gives me a z-score of negative 0.67. Now once I go to find this z-score on the right hand side, The only thing that's going to change is this area. Instead of using 0.25, I should now use 0.75. Interesting. Your z-score was 0.67. Now this will always be the case because your normal curve is symmetric. Once you've found your lower z-score, your upper z-score should be the same numbers but just positive instead of negative. So you really only ever have to calculate one of them. Now my question's asking me for what SAT scores represent the middle 50%. And so far I only have z-scores. So I'm going to have to convert these z-scores into SAT scores. So the first thing I'll think about is my z-score formula. I know the z-score for the lower SAT score should be a negative 0.67. I don't know this individual SAT score, that's what I'm trying to find, but they give me the mean and the standard deviation. From here, all I need to do is solve for y. So to do that, I'll take the negative 0.67, multiply by 100, and then add 500 to get y by itself. And I found the lower SAT score to be 433. We're going to do the same thing then with the upper z-score of 0.67. Which gives us an SAT score of 567. These two scores here represent the middle 50% of our data. Go ahead and pause your video, try these three on your own, and then once you've completed it, press play to check your answers. Here are the answers for A, B, and C. Please check and make sure that your answers match mine. Yesterday we started discussing the condition of the nearly normal model. So I want to talk a little bit about how to check and see if your data does meet that condition. So when you actually have your own data, you must check to see whether a normal model is reasonable. Looking at a histogram of the data is a good way to check that the underlying distribution is roughly unimodal and symmetric. And we say roughly there because it might not be perfect, but it should be pretty darn close. Okay, there's a more specialized graphical display that you can use, and it's called a normal probability plot. If the distribution of the data is roughly normal, the normal probability plot approximates a diagonal straight line. If your normal probability plot shows this straight line, then it means that your distribution is normal. Any deviations away from that straight line show that it is not normal. So for your example here, we have a histogram and it's looking pretty unimodal and symmetric, maybe a couple of possible outliers, but I'm thinking that it's pretty normal there. And then here's your probability plot. You can see that most of your dots here are following that diagonal straight line. Again, you can see these outliers that may kind of give you worry, but generally speaking, it does follow that straight line. So on this example here, agility test scores were given. We want to determine if the data is normally distributed. So the first thing that we'll do is type our data into our L1, and then we want to create either a histogram or a normal probability plot. I'm going to show you how to do both of those. So the first thing I need to do is get to my stat plot. I want to make sure that my plot is on, and I'm going to start with just kind of making a histogram. Again, my data is pulling from L1, and I can press zoom 9. to get my histogram. Now, it's kind of hard to tell on this histogram. It does look like it's possibly skewed to the right, but there's not a whole lot of data, so it can be a little bit harder to read those histograms. If we go back to our stat plot, this first one here looks like a normal probability plot. This is actually a scatter plot, which we'll talk about next unit. Your normal probability plot is this very last graph. So once I'm there, make sure that your data is coming from L1. You can hit zoom 9 and it gives you your normal probability plot. So I would just sketch that on here. It doesn't have to be perfect, but it should give you a relative idea. Now, this question asked us to determine if the data is normally distributed. There are quite a few curves in this normal probability plot, and our histogram looked skewed as well, so I would say that this data is not normally distributed. On this next example, we are going to put everything together. So it tells us there are 12 competitors' times for the men's alpine downhill race during the 2006 Winter Olympics. Based on the data presented, what percent of all Olympic times will be less than 109.78 seconds? So the first thing I want to do is make sure the data is normal. So I have typed all of my data into my L1 here, and I'm going to create that normal probability plot. It looks like things are looking pretty straight. There might be one kind of outlier out here, but generally speaking, things are looking normal. So I'm just going to kind of sketch that normal probability plot. Just label it normal probability plot. Looks straight. So a normal model is appropriate. From here, I can start working to answer that question. So it says, what percent of all Olympic times will be less than 109.78? I want to draw my picture of my normal curve using the normal model, so my mean is 0 and my standard deviation is 1. Now I don't have a z-score yet, so the first thing I'll need to do is convert this 109.78 into a z-score. And in order to do that, I need my mean and standard deviation, which they didn't give me. So I'll have to go back to my calculator to find that mean and standard deviation. I already have my data in my L1, so I can go to stat, calculate one variable stats, and that tells me that my mean was 111.07 with a standard deviation of 1.57. From here, I'm good to go to start calculating the z-score. And I got a z-score of negative 0.82. So negative 0.82 is going to be roughly here. I'm looking for less than, so I'm shading everything to the left. And now I can use my normal CDF because I'm looking for the area, the percentage. My lower bound should be a very small number. My upper bound is the negative 0.82, and my mean and standard deviation are staying 0 and 1. And we get 20.61 as our final answer. It's very rare that you'll be asked to do all of this together as we just did in this last example. Usually they only want kind of the last little piece here, but it is nice to spend some time with the raw data, going back and putting it all together.